The universe, as we understand it today, is a vast space full of stars, galaxies and possibly countless planets. With our state-of-the-art instruments, we can peer deep into this cosmic ocean and reveal an incredible variety of celestial bodies. Despite these profound insights, we are still limited by the observable universe. Beyond this visible horizon is a much larger space, perhaps part of a larger multiverse. Our scientific efforts have revealed many details about the universe we inhabit, but one great mystery remains unsolved: the existence of life beyond Earth. Despite rigorous searches, we have yet to find even the simplest forms of extraterrestrial life, let alone intelligent beings. This mystery raises one of humanity's deepest questions: are we alone in the universe? The answer to this question involves several possible scenarios. We could live in a universe where intelligent life is common, scattered among the stars and galaxies, or we could be the only intelligent beings in this outer space. To solve this basic question, it is necessary to significantly improve your knowledge. The process of achieving this involves distinguishing between what we know to be true, what we expect from current knowledge, and what remains unknown. Let us first examine what we know to be true. It includes significant achievements in both experimental and observational astronomy, supported by concrete evidence as well as theoretical extrapolations of our best scientific theories. In recent decades, we have gained a lot of information about the structure and content of the universe. For example, we now understand the number of stars in the Milky Way and other galaxies, the distribution of Sun-like stars, and the potential of those stars to host rocky, potentially habitable planets. There are about 400 billion stars in our Milky Way. This figure emphasizes the sheer scale of even a single galaxy. However, the Milky Way is just one galaxy among billions in the observable universe. By studying the metallicity of stars, mainly the ratio of heavy elements compared to hydrogen and helium, we can estimate the likelihood that they host planets. Stars with higher metallicities are more likely to have rocky planets, which are considered the best candidates to harbor life. In addition, we classify stars by their mass and spectral type to determine which could potentially host Earth-like planets. These Earth-like planets are defined as rocky planets of similar size and mass to Earth that lie in their star's habitable zone, the region where conditions can allow liquid water, an essential ingredient for life. Know that the knowledge we have accumulated over the past 30 years is remarkable. We have gone from not knowing if there are planets outside our solar system to confirming the existence of thousands of exoplanets, some of which are in the habitable zone of their stars. In addition to these insights, we have estimates of the number of potentially habitable worlds in the observable universe. These estimates are based on our understanding of star formation, galaxy evolution, and theoretical predictions about galaxies that are difficult to directly observe. For example, we know that there are about 2.2 sextillion stars in the observable universe, a number so large that it is difficult to fully understand. These stars are dominated by different types of stars, including Sun-like stars, G-type, cooler and less massive K-type stars, and abundant red dwarf stars, M-type, which make up most of our stars. Galaxy. Stars with sufficient metallicity, about 98% of known planets orbit stars with that property, are likely candidates to host planets. Even with these criteria in place, the number of potentially habitable planets is staggering. It is estimated that there may be approximately 10 to the power of 19 such planets in the observable universe. However, this chapter assumes that we had incredibly advanced technology to detect and explore these worlds. To advance our understanding, scientists often rely on speculation because there is no direct evidence outside of our solar system. One of the main assumptions is that life arose from non-life through natural processes, given the right conditions and chemical ingredients. Although widely accepted by scientists, this assumption is not without controversy. This assumes that life can arise on any planet with similar conditions to Earth or even different but favorable environments. Another assumption is that the basic laws of physics are universal and apply equally throughout the cosmos. This includes the processes that lead to the formation of stars and planets, the chemical reactions that can give rise to life, and the evolutionary mechanisms that drive biodiversity. We also assume that life contains its basic organisms capable of taking energy from their environment, using that energy for metabolic processes, and reproducing or producing related offspring. Cosmologically, the unobservable parts of the universe are assumed to follow the same basic principles
Delta
as the
rocket
observable
carrying
parts.
GLAST, a gamma-ray
This includes the
telescope
belief that
searching
the
for unseen
processes leading
physics
to the
in
Big
the stars
Bang,
of the
particularly
galaxy.
cosmic inflation, occurred on a much larger scale than our observable universe. This assumption suggests that there are many regions of the universe beyond our observable range that are full of galaxies, stars, and possibly life similar to our own observable universe. From these assumptions comes the idea of a multiverse, or a large number of separate universes. Each of these universes may contain its own galaxies, stars, and possibly life forms. Although we can observe only a small part of the universe, the part in our light cone since the Big Bang, the theoretical framework supports the existence of vast unobserved space beyond. Despite these assumptions, many questions remain unanswered. For example, we still do not understand the precise mechanisms by which life on Earth arose from non-life. Theories such as peptide RNA coevolution suggest that amino acids and nucleic acids may have formed spontaneously in the presence of water and natural energy sources, leading to the first living organisms. However, this is speculation without concrete evidence. Moreover, we do not know how often life, once it appears, can last for long periods or develop into complex and diverse forms. The history of life on Earth offers some clues, but this is just one example. Life on Earth appeared relatively early, no later than 3.8 billion years ago, and continued to evolve into a large number of complex organisms, including intelligent beings such as humans. If these processes are common, intelligent life may be widespread. If they are rare, we may indeed be alone. The prospect of finding extraterrestrial life, whether simple or complex, intelligent or microbial, is the driving force behind many scientific endeavors. While our primary interest may be the discovery of intelligent, technologically advanced species, the discovery of any life form would be monumental. Even microbial life on another planet suggests that life is not unique to Earth and may be more common than we currently believe. In 1950, physicist Enrico Fermi asked the famous question, "Where is everything?" A question that encapsulates the Fermi Paradox. Despite the apparent abundance of the ingredients necessary for life throughout the universe, we have yet to encounter any evidence of extraterrestrial civilizations. This paradox remains a great mystery to scientists and has led to various hypotheses trying to explain the apparent silence. One of the pioneering approaches to solving this question was the Drake equation, formulated by Frank Drake in 1961. The purpose of the Drake equation was to estimate the number of technologically advanced civilizations in our galaxy by multiplying several factors, including of the number of stars. Formation, the fraction of stars and planets, the fraction of planets from which life originates, the fraction of life-bearing planets on which intelligent life develops, the fraction of intelligent civilizations capable of interstellar communication, and the observable time of those civilizations. Although groundbreaking, the Drake equation has become less powerful over time due to a number of unspoken assumptions that are inconsistent with modern understanding. For example, the equation assumes that only one planet per star system can support life, that intelligent life will never spread to other worlds, and that interstellar communication would primarily involve radio signals. These assumptions have been challenged by new discoveries and advances in our understanding of the universe. Today we have an even more precise approach to estimating the number of possible habitable worlds and intelligent civilizations. Let's start with the number of stars in our galaxy, which is estimated at 200 to 400 billion. Exoplanet research has shown that almost all stars have planets, and many of these planets are located in the habitable zone of their star. Among the various classes of stars, Sun-like, G-type, stars are considered the main candidates for hosting life, but other types, such as K and M-type stars, may also have habitable planets. The fraction of stars that have habitable conditions is crucial. While massive stars may return too quickly to develop intelligent life, lower mass stars, especially M-type red dwarfs, are abundant and long-lived.